We are back with a new session today. As we have completed the laws of motion, friction, circular motion, all these chapters we have already completed. We have done the problems of the theory part of banking also. I'll take up some small problems related to laws of motions and a few problems related to friction. Okay. Let me start with this problem. These are all problems of moderate difficulty level, not a very high difficulty level. But then it did appear in joint entrance exam in various years. Okay, let us take a small problem. It is given a 34 meter long ladder weighing 10 kg leans on a frictionless wall. Its feet rest on the floor 3 meter away from the wall as shown in the figure. If FF and FW are the reaction force of the wall and the wall, of the floor and the wall, then the ratio of FW by FF will be. We have to find the ratio of FW by FF as it is given here. Okay, so how to do that? One very important thing that you should note out here, one very important thing is that it is given that it leans on a frictionless wall. So the wall is frictionless. Okay, the floor is not. So wall is frictionless. So this point we must underline that wall is frictionless, floor is not. Okay, we have to take these things very seriously. Okay, if I redraw the same sketch once again, then we can find that if here, if I just do it like this is A, B, C. Here AB is the ladder. Okay, AB is the ladder. Okay, which is leaning like this. Okay, and here we can say that this is point A, B, C, and here what is the mass given here? It is 10 kg. So from the center of mass, let us give a 10 kg load over there. Okay, what is given like here the reaction force, in the top side. Let me just rub this thing a bit. I'll say that this point is B, and the reaction force here up, it is FF. Reaction force FF means F, small f from the floor. Okay, and here there is a reaction force. I'll just rub this thing as well. Here there is a reaction force FW. This point is A. Okay, this was given to be, this point was given to be root 34 meter, and any other thing is given, root 34 meter, and this distance is given to be 3 meter. Okay, so if this is leaning, the vertical portion, it is frictionless, but then friction is there in the floor. So as it is leaning down, it will have a tendency to go down. Like there can be a new position, like it has, the ladder has become like this. You know, the ladder has become like this. It is sliding down. Okay, so as it is going down, there will be a component of friction that will be towards the left. So that I am writing as small f. Need not confuse this small f with FF. Okay, this particular F denotes the floor, but this F denotes the friction. This is friction. Okay, so okay. Now what you can do, will just apply Pythagoras theorem to find out the length of AC. So root over 34 whole square is equal to 3 square plus AC square. So AC turns out to be 5 meter. AC turns out to be 5 meters. Okay, so this we got 5 meters. Okay, now what? Now F is the friction force. Now I'll just apply initially some basic things like if I'm doing that sigma fx equal to 0, sigma fx equal to 0, then we can find that small f is fw and sigma fy equal to 0. In this case, we can find that ff is the reaction force from the floor to the ladder. ff is up minus 10 kg into acceleration. So this is equal to 0. What is this 10 kg? This is what is given to us. So this is mass into acceleration down. Okay. So this is one equation. This is equation number 2. Now what we can do, we can take a moment about the point C. Okay. Taking moment about C. What are the equations that are known to us? We can write for the equilibrium equation sigma fx equal to 0. That is sum of all the forces in the horizontal component is 0. Sigma fy equal to 0 and moment about any particular point is 0. So these are the three equations we can apply for an item to be in the state of steady state equilibrium. So these are the things. That is why we are writing that taking moment about the point C. Okay. So taking moment about the point C, we can write that what all are the forces that can come? That ff, this ff into 3, ff into 3 will be clockwise. See this diagram? ff is up into 3 clockwise. Okay. And fw into 5 will be anti-clockwise about C. Minus fw into 5. Okay. Anything else? Like that 10 kg is coming. So 10 kg into 10. G we are considering to be 10. So 10 kg into 10 is 100. So 100 into 3 by 2. Because if it is coming down here, this distance is 3 by 2. So minus 100 into 3 by 2 is 0. This is equation 4. So ff into 3 is clockwise. Fw into 5 is anti-clockwise, negative. 100 into 3 by 2 is anti-clockwise, negative. Okay, so this is one equation. Now I'll take moment about the point B. If I take moment about the point B, then ff and small f, that will go because that is being applied at the same point. So taking moment about the point B, what all will come? We have FW into 5 it will come. FW into 5 will be anti-clockwise. So minus FW into 5 minus FW into 5. Then it is anti-clockwise and 100, that is 10 into 10 plus 10 into 10 into 3 by 2 will be plus because this is clockwise. So minus Fw into 5 is anti-clockwise, 10 into 10 into 3 by 2 is clockwise, is equal to 0. So this is equation number 5. Okay. So we have this many equations. If you just solve it from this equation, we get Fw comes out to be 30 Newton. Okay. And if you put it in the equation number 4, Ff comes to be around 100 Newton, and we have to find out Fw by Ff, that is 30 by 100 is equal to 3 by 10. Okay. The closest answer is 3 by root over 109. Okay, that is the closest which I got. Okay, so the steps you got here, we have to be first very clear that the vertical wall is smooth only, but the floor is rough. So as the floor is rough, there will be a friction force on the right side because the ladder will have a tendency to lean in the left side. It is leaning to the left, so the friction will act opposite to the direction of motion. The friction will be on the right side. So thereby, we're just forming those equations and solving. Okay. So this is done. Then we'll go to the next one. Next one, what is given here? A string of negligible mass. A string, I'll just take it a little bit this side. Okay. A string of negligible mass going over a clamped pulley of mass small m supports a block of mass capital M. Okay. The pulley is having a mass of small m. It is supporting a block of mass capital M as shown in figure. The force on the pulley by the clamp. So there will be a reaction force. The force on the pulley by the clamp is given by one of the four options. Okay. So the reaction force, let me draw the free body diagram of the pulley alone. Okay. Free body diagram of the pulley alone. So if I just draw the pulley, let's say this is the pulley, and I'll mark a center for this. Okay. And first I'll just mark the mg. The small m is the mass of the pulley. Capital M is the mass which the pulley is supporting. So small m will be down. That is my first consideration. Let me first put small mg down. Okay. Then we have a tension. Then we have a tension that is T. Okay. And this tension will be equal to capital Mg, that is what is the mass it is supporting. We have a tension, the same where is going this side also. So tension equal to Mg will be on this side also, and we have a reaction force. Let me we have a reaction force. 1 second. Okay, we have a reaction force R. That is, of course, it is connecting from the clamp to the pulley. We have a reaction force. So this is how the arrangement is. Okay, this is how the arrangement is. What all the forces, you can see it here. Okay, now R is the resultant force. Let me just write it down. Capital R is the resultant force. Capital R is the resultant force from the clamp to the resultant force from the clamp to the pulley. Okay. So okay, from the clamp to the pulley. Now what you can do is what are the horizontal forces coming? Horizontal forces. So horizontal force that is coming over here, that is equal to T equal to mg. That top horizontal component is acting but in the negative side, so minus mg into I. I'm writing vectorically, so minus mg into I is the horizontal force that is acting. So we are saying that this is the horizontal component that is acting on the pulley. What is the vertical component? Vertical force. Vertical component is T equal to mg, that is acting down. So minus mg into j, that is coming down, minus mg into j, where small m is the mass of the pulley that is coming down. So this is my vertical component. Now, if I am just writing here as minus m plus m into g into vector j. Okay, what is the resultant? For the resultant, as they are vector quantities, so triangle rule applies. So if I am just drawing the triangle for you, so this will be my horizontal component, and from the tip of horizontal component, the vertical component is going down. So from here, there will be a vertical component, that is V. And if I am just closing the triangle, so this will, if I am just closing the triangle, so this will be my resultant vector. R is equal to H plus V. So R is equal to, that is the triangle rule for vector addition, H plus V. And so we have already got what all are the values. So R is minus mgi minus m plus m g, and this is j. Okay. So what will be the resultant? Resultant mod, the mod value is square root of mg square plus this will be actually minus m plus m g whole square. So this becomes g, let me take it out. So this becomes m square plus m whole square. So this will be the mod of r, or I'll just say this is how we are getting. Okay, which answer it is matching with? Plus capital M square. Okay, this is number 4. Okay. So that is how we are bringing it. You just got to know how it is to be solved. Just draw the free body diagram of the pulley. And just find out equate the horizontal and vertical component of the forces. Then just bring it down into the triangle law of vectors and then just do the addition. You'll find the resultant. Fine. So that is how we are solving the net reaction forces. Then we come just in the next problem. Here, one thing we should note that the direction of R, that is that what we have given, the direction will be actually, that is the action. Okay, this direction is different. What I shown here that R, it is from the clamp to the pulley, that is acting from the clamp. But then if you draw the free body diagram of the pulley alone, this direction will be different. This direction of R, what is drawn here, that will be down. Okay. This area I am pointing towards. Okay. This direction will be down because we are taking the free body diagram. Okay. If you at all want to match these directions, like this direction of R along with this direction, you can just correlate why this resultant component of R, it is going down. Okay. Because if you take the free body diagram, then it is the R in the upside is the action, but here R is the downside, is the reaction. So we must take the reaction here. That is why the free body diagram, the closing vector is the resultant, and that is matching with the free body diagram of the pulley. Okay. So make this slight change. Okay, or whatever we have drawn earlier. Okay. Next one is this problem. I'll just take it a little bit this side. Okay, what is given there? It is given that as per the given figure, a weightless pulley P, the pulley is at the center top. The weightless pulley P is attached on a double inclined frictional surfaces. Okay, friction will be there. Double inclined frictional surfaces. The tension in the string will be, the tension in the string we are to find out. How to find the tension in the string? Uh, there is a small check here. It is just a typing error. Double inclined, it will be frictionless surface. Otherwise, mu should have been given. So this please make a correction here. This one, this is not frictional. This is frictionless. Mu will not be considered. Okay, so this is frictionless. Otherwise, if it is having friction, then mu will be given. Mu will be given in your free body diagram. We have to consider the friction also for the force calculations. Okay, but right now we are just neglecting frictions and we'll draw the free body diagram. Okay, let me redraw the sketch once again. Two inclined surfaces are there. Two inclined surfaces are there. There is a one body lies here. Here is the pulley, and it is attached with a string like this, and here also there will be another mass and it is attached with a string. Okay, now it is given that this is your 4 kg and this is 1 kg. So we will have a consideration that 4 kg is going to the left. So 4 kg is going down and 1 kg is being pulled up. Okay, so this angle, this is 60 degree, and this angle, it is 30 degree. Let us assume the floor is fixed. Okay, so for doing the free body diagram, let us first say we know one thing, that from the 4 kg mg is down, so 4 into g will be down here, 1g will be down. Okay, and here we have a component. So if I just draw the normal component here and the normal component here, we know that this is also 60 degree and this is 30 degree. 30 degree. So we have a component here like 4g cos 60 here. Here we have a component 1g cos 30, and we have a component going down, that is 4g sin 60. Here we have a component that is that will act. We have a component, so this component will actually act in the upside directions, in this direction. So because it is going up, so 1g sin 30. Now this 4g sin 60, that component is actually bringing, that is instrumental in bringing the 4 kg mass down. Okay, and there will be tension in the string also. So the tension will the string, so this will be tension always directing towards the pulley. So tension up, here also tension up. Now what we can do, that if you apply Newton's second law, the acceleration, let the acceleration, let the acceleration of both the masses to be A. Okay. Apply Newton's second law. If you apply Newton's second law, we can write that 4g sin 60 is actually bringing it down. So 4g sin 60, 4g sin 60, that is this one, 4g sin 60 minus t. 4g sine 60 minus t, the body is going down, so that should be equal to 4 into a. So this is my equation 1. And this is going up, so we can write that, so on the other side, on the right side, t is greater than mg sine 30. So this component will actually be on the right side. Okay, so this, let me just correct it. One g sine 30. Okay, so if you just draw it, that t is up minus 1g sine 30 is equal to 1a. So these are the two equations we got. So two equations, we have two unknowns. One is t, that is the tension. One is a, that is the acceleration. If I solve these two equations, we are getting a to be 4 root 3 minus 1, and t we are getting 4 into root 3 plus 1 Newton. Okay, this is meter per second squared. So these are the two equations which are very important for this type of problem. You have to just find out which mass will be going down. So as the left side 4 kg is going down, so 4g sine 60 must be greater than t, and the difference in vector, that if it is equal, then acceleration will not be there. It is unequal, then only acceleration acts, Newton's second law. So 4g sine 60 is greater than t, that is why 4g sine 60 minus t is equal to mass into acceleration. And in the right side, the mass is going up, so tension T must be greater than 1g sine 30. So T minus 1g sine 30 is equal to mass into acceleration, that is 1 into a. We have two equations, two unknowns. Only capital T, that is the tension, and the small accelerations are the unknown, so that we can solve it out. Okay. Okay, we'll just see the next problem. Okay, this is also a pulley type of problem. The problem is very interesting. Here we are given two pulleys. You are given two pulleys. One is on the left side 8 kg, another is on the right side 2 kg. There is a gap from the 8 kg pulley from the floor, that is 20 centimeter. What is given here? The boxes of mass 2 kg and 8 kg are connected by massless string passing over a smooth pulley. Calculate the time taken by the box of mass 8 kg to strike the ground starting from rest. So time taken by the box of mass 8 kg to strike the ground starting from rest. Okay, kinematics also is required here. Kinematics is later, but then first we have to find out at what acceleration the 8 kg mass is actually coming down. Okay, so here what a simple thing, let me just tell you one thing. If I draw a simple pulley system before solving, okay, so if I draw a pulley like this, let's say this is the pulley, and one side there is a mass, other side there is mass m1, let's say. Okay, and this is also tension, this is also tension. Okay, T is the tension in the string. Okay, so here we can say that the block, the one is going up, one is going down. If I say that the block M, the block M goes up by distance x, then the block M1 goes down by x also. So what will be the total work? The total work is T into x plus T into x. Okay, that is 0. The total work is 0 because the one is going up. This will be minus. You can take that if you take the distance. One is going up, one is going down. The total work done in the system is 0. Because the left hand side pulley, both are experiencing tension in the upside direction. The left hand side pulley, if it is going up by a distance x, the right side is going down by a distance x. So the total work done is 0. Vice versa, you can do it otherwise also. Okay, so we can write that sigma t into x is 0. The summation of total work done is 0. If I just differentiate once, then t into x dot is 0. Okay, x dot is dx by dt. So then x dot becomes velocity. So t into velocity is 0. If I differentiate it once again, so sigma t into x double dot is 0. So x double dot is d2x by dt square, that is acceleration. So this is velocity and acceleration. Okay, so thereby you can write that sigma t into a is also 0. So we will apply this over there to find out the acceleration, because here in our problem you see the 8 kg pulley, it is supposed to go down and 2 kg will go up. But what will be the acceleration? It is in a 2 pulley case system, but this what we have found out, it applies there also, because it is all connected. It is not disconnected. It is not discrete. It is continuous. So it applies there also. Now these things we will apply it and find out the accelerations. Okay. So what we can write, let me in this particular sketch, let me say that if this is t, in this figure itself, I'll just mark certain things. Let's say if this is t, this is also t. Out here also this is also t. Okay, we can make these things. Now if that be the case, then out here we can make it as 2t. Okay, so and let's say this is going down. We'll find out the accelerations, then we can just see how we have got it. The acceleration things, if I just say that here sigma t into a is 0, as we have got there, sigma t into a. So 2t, here 2t into a1 plus t into a2, it is 0. Okay, so 2t into a1, so I'm considering that this is going down by a1 and this is going up by a2. So 2t into a1 plus t into a2 is 0. Okay, we are seeing that 2a1 is equal to a2, or okay, sorry, this becomes minus, so I'll just make it negative. 2a1 is minus a2. Okay, so a2 is minus 2a1. It only says that both the accelerations are of different signs. So a1 is down, a2 is up. That is why minus. Okay. For the time being, so what we can say, that if I just remove the a1, a2, I can simply write that in both the cases, can we not now write that if this is the block 8 kg, 8 kg is coming down by A, then 2 kg is going up by 2A. Is it clear? Let me just highlight these things. If A2 becomes minus 2A1, A2 was the case for the 2 kg and A1 was for 8 kg. Now I can just simply mark here, both the accelerations are same, of course, because they are connected by the pulley systems. Okay, so if this is coming down by A, so the 2 kg will go up by 2A. Okay, once that is known to us, this particular thing, I hope it is clear. Okay, this is 8 kg is going down by A, 2 kg is going up by 2A. So if this system is clear, then we can apply these things further. Then we can apply, let me just write it down once. Thus we assign, A to 8 kg and 2A to 2 kg. Okay, here we can write that now just simply the summation of the forces, that is 8 kg. So 8 into 10, acceleration due to gravity is 10. So 80 minus 2t is equal to 8a. That is equation number 1. This is simply mg. Okay, mg. So mg is down, 2t is up. So it is facing an acceleration. This thing is clear, no? That is, this I can rewrite that mg minus 2t is mass into acceleration. This is only written out here. Okay. So it is mg minus 2t, not 2t minus mg, because it is going down. So mg must be greater than 2t. That is why mg minus 2t, not 2t minus mg. That is equal to mass into acceleration, Newton's second law. That is equation number 1. Okay. And for equation number 2 on the other side, we can write down as t is now greater, t minus mg. So t minus 20, that was 2 kg. So 2 into 10. So t minus 20, that is equal to your 2 kg into 2a, because that is going up by 2a. Okay. So this also you understood, no? This is 2a because that was going up by 2a. This was going down by a, that was going up by 2a. That is why I have written down. So this equation now stands out. So solving this 2 equation, we are getting the value of a to be 10 by 4 meter per second square. And then if I apply kinematics, that s equal to ut plus half at square, u will be 0 because it is starting from rest. So u equal to 0. S is given to us. 20 centimeter. 20 centimeter is the distance from the 8 kg block to the floor. So 20 centimeter it is given to us. Okay. So this is given to us. Now if I just write down from here that we are told to find the time. So t square is equal to 2s by a. So t is equal to root over 2s by a. A you have already got it. 2s by a. Okay, a you have already got it. So this comes out to be 0.4 second. This type of thing you can apply to any pulley problem to find out the acceleration of one is going down, one is going up. These things, it is just we have to understand one thing, that sigma t equal to a is 0. Okay. It came from the fact that total work done by the pulley system is 0. That is why sigma t equal to a, we can do it. I have done one differentiation. T into x dot is 0, then summation of t into x double dot is 0. Okay, then you can find out this thing. Okay, so t is coming to 0.4 second. That is the time taken for the 8 kg block to come down. Okay, okay. Next one. I'll just take it little bit this side. Okay. Next one, what it has told that. As shown in the figure, a block of mass 10 kg, lying on a horizontal surface is pulled by a force F acting at an angle of 30 degree with the horizontal. Mu s is given, so the floor is no longer frictionless, it is rough. Mu s is given. The block will just start to move for the value. Of F. The block will just start to move. So it is still under rest. So acceleration is not there. So under what value of F the block will just start to move? Okay, friction was limiting it. So it was the limiting friction. We already studied about limiting frictions. Okay, so if you apply, if F crosses a particular limit, then only the block will start to move. Okay, so we'll consider the acceleration to be zero in this case. Please read the problem once again. Okay, it is important to understand. So let me draw the diagram what is given. Let me just redraw the diagram once again, then things will be clear. So this is my floor. A block is resting on the floor. What is the mass given? 10 kg. Okay, let's say this is the mass. A force is applied at an angle of 30 degree. So let me just simply draw two components of the force. One is the horizontal component F cos 30. We have a vertical component F sin 30. Okay, two components. Mg will be down. Mg will be down. Reaction force is up, and it will have a tendency to go right. That is why a friction also will come. That is small f to the left. Okay, these are the things that will come in the problem. Okay, so let me just write it. First is if I take the vertical component to be 0, so sigma fy equal to 0 if I do, then what all are the components coming down? Like n is acting up, so capital N will be plus f sin theta is up, so plus f sin theta is also in the upside. What else? Mg is down, minus Mg is 0. So this is equation 1. And if I draw the sigma fx equal to 0, first is f cos theta. F cos theta is positive, acting on the right side. Friction is on the left side, so minus f. Okay, friction is on the left side is equal to, if I say that one acceleration acts, but that acceleration will be 0, so that will be mass into ax. But in this case, this particular component is 0 because it is still on rest. It is just start to move, so it is still on rest. So here we can simply write that f cos 30 degree is equal to mu s into n. Okay, this we can write mu s into n. So this will be my equation. This will be my equation 2. Now if I just substitute the value of n from equation 1 and 2, from equation 1 and 2, we can get the value of f to be 25.2 Newton. Okay, 25.2 Newton. That is what was asked to us, that the block will start to move for what value of f? The block was in a state of rest. What will be the value of f to make it to just move? So the value of f will be 25.2 Newton. Okay. So for this video, let me limit to only this 5 problems. Okay, there are furthermore, there are 6 to 7 more problems. Okay, I have a bank of about 103 problems for this chapter of friction and laws of motion. Circular motion, of course, we can take it at a later part. You can shoot a mail to me in niloyforphysics@gmail.com for a live class of about 2-hour duration. Then we can go on solving the problems. Okay, and we can interact with you. It is more important to interact because if you have any difficulty, you can ask me in the live class. Okay. Should you have any problems, so you can just write in the comment box that you want a live class regarding this chapter. Okay, we can always schedule a time for that. Thanks for watching. Thank you.